Hello, this is Mr. Stansbury. I'm going to take you through the notes on analyze graphs of polynomial functions. At the end of this, you should be able to say, I can use intercept form to graph and analyze polynomial functions, and I can describe the characteristics of a parent polynomial function. Okay, so let's take a look at some important info here. So first thing is turning point. Turning point is where a graph changes from going up to going down as you move left to right, and vice versa. So it could be going down to going up. So turning point would be right here. It stops going up and then starts going down. And then here's another turning point. It stops going down and starts going up. Okay. Extrema is the highest or lowest the graph will be. That's the general for extrema. And we call it a global minimum or maximum is the highest or lowest the graph will ever be. And then a local minimum or maximum is the highest or lowest the graph will be in an area. So for example, this here is a local maximum because it's the highest in the area, but it's not the highest it will ever be. This here is a global max because it's the highest the graph ever gets. This is a local minimum because it's the lowest it is in this area, but it's not the lowest ever on the graph. This is the global minimum because that's the lowest it ever gets. Okay? Okay. Let's take a look at an example here. We've got three different functions, all given with the equations up here and all with the graph. So, number of distinct factors. If we look at the equation, basically they're saying how many different ways can we make this equal, make this be true. And the factors, we got to make it equal to 0. So it's basically 0. Oops, got to change the pen color. So how often does 0 equals x cubed? Only one factor works, and that's 0. 0 cubed is the only one that's going to make this work. So there is one distinct factor. Okay, and then over here, how many distinct factors we could put in? So 0 equals x squared times x minus 1. So if you have multiple things multiplied together to end up equaling 0, as long as one of those in there is 0, then it will be true. So we could have 0 in there for one of the factors, or we could also have 1, because 1 minus 1 is 0. 0 times 1 squared still gives us 0. So we need to make this equal to 0, and we need to make that equal to 0, so that gives us two distinct factors. And then over here, we could make that equal to 0. What minus 1 gives us 0? 1. And then what plus 1 gives us 0? Negative 1. So we have three distinct factors there. Okay? So if you look on the graph, how many x-intercepts does this have? 1. And where's it at? It is at 0, 0. And notice that we figured out that x had to be 0. How many x-intercepts there? So it goes up and just touches right there. So we call that an x-intercept. So that's going to be 2. And they are at, one of them's at 0, 0. Right? So there's how we got, remember we could plug in 0 there or 1 there. So 0 and 1 were our two spots. So we can also see that it crosses here at 1. Right, and at 1, 0. Right, and then how many total x-intercepts here? There's 1 there, 1 there, and 1 there. So there's 3, just like we said here, and because there's 3 different spots, 3 different ways we can set it equal to 0. So 0, 0 is right there. Negative 1, 0 is right here, and then this one over here is 1, 0. So 3 different spots. Okay. And then last thing to take a look at in here is turning points. Turning points is when it stops going up and starts going down, or stops going down and starts going up, right? So it's basically changing direction. So this one doesn't really truly have a turning point, but right here is a point of inflection. So really there's no turning points, but we can say there is one inflection point. Point. Okay, How many different turning points here? There's a maximum there, and there's a minimum there. That's basically what you're looking for. Looking for how many maximum and minimums do you have? That's your number of turning points, right? So we've got 2 turning points there, right? And those are at 0, 0. And then this looks like it's at, we don't know exactly. We'll call that at, say, 0.5 and negative 0. We'll call it 3. We're just guessing, and we don't have to have exact here. They don't even actually ask you to list those off. We're just kind of showing it so that we can get that figured out. How many turning points here? 1, 2 turning points there. And those are at, like, say, negative 0.6 and 1, it looks like, roughly. And then we also have one at 0, 0. And then we also have one here, it looks like, at about a half and negative 0.6, we'll call it. Oh, oops, I put 1, negative 0.6 and 1. Okay, that's right. So this one is 0.5 and negative 0.7 or 6, whatever. We're just so you can kind of get an idea of where it's actually at. Okay? Okay. Next thing. Example 2. Okay, so first thing we're going to do is just fill in this like we just filled in the other table. And if you'll notice, this is to the 4th power. There's 3x to the 3rd plus another x. So this is to the 4th power, and that's x squared times another x times another x. These are all to the 4th powers, just to let you know. Okay, number of distinct factors. There's only one distinct factor, and that's going to be at 0, right? And then how many different distinct factors do we have here? We can put 0 in here for that, and that would work. And then we can also do 1. So we've got 0 over here. We've got 0 and 1 there, so there's 2. And then we can do 0 here, positive 1, or negative, not 2, negative 1 in all 3 of those. So there's 3 distinct factors. How many x-intercepts are there? There's just 1, and that's at 0, 0. How many x-intercepts here? 1, 2. And those are, we know what the x values of both of these are going to be because we figured out what the x values have to be, right? So 0 and 1. So 0 looks like that's at 0, 0, and then 1 looks at like it is at, also it's got to obviously be at 0. And then how many x-intercepts here? 1, 2, 3. And those are at negative 1, 0, 0, 0, and 1, 0, right? And then turning points. There's just 1, right? And that's at 0, 0 right here. Turning points, there's really only one turning point, but there's also a point of inflection as well. So this here, turning point, and then this here is what we call the point of inflection, right? So officially 1, but there's also aldos, wow, also 1 inflection point. Okay, and then this one here, how many turning points? There's 1, 2, 3 different turning points, right? And we don't even have to worry about putting those in, but there are 3 different turning points on that, okay? Because we got a minimum, maximum, minimum, so 3 turning points, okay? Now, let's answer a few questions here, and then away we go. But before we do that, let's take a quick little comedy break.
And you wonder why women mature faster than boys. While we playing with make-believe stuff like Ninja Turtles, you learn how to take care of babies. And cooking little brownies with light bulbs and stuff is stupid. Don't act like you ain't had that easy bake ridiculousness. It takes 6 weeks to make a brownie in that silly thing. It's a good brownie, though. It wasn't... It wasn't done in the middle. It was a good brownie.
Okay. Okay, so examine your tables. What seems to determine the number of x-intercepts that the graph of a polynomial function has? Is there any connection to the degree of the polynomial? So number of x-intercepts. Is there a connection to the degree of the polynomial? Well, yes and no. It just kind of depends. Like, so this is x to the 4. So really it's how many different factors there are. So notice, look, there's only one possible factor here. There's two possible factors here, and there's 1, 2, 3 possible factors here. So that's where our x-intercepts are coming from, right? So the number of distinct factors is the same as the x-intercepts, okay? And then the degree, since these are all 4th degree, the most the most solutions you could possibly have. So we could have possibly one more if this was, you know, like x minus 1, x plus 1, x minus 2, x plus 2. So the most we could possibly have is 4, which is the same as the degree of the polynomial, okay? Okay, so just wrote those down, what we were just talking about. B, what observations can you make about the degree of a polynomial function and the number of turning points its graph can have? How is this related to the total number of extrema indicated by the graph? Okay, so really what that means is the maximum number of turning points, like this one here has got the max amount of turning points. And that is 1, 2, 3, which is 1 less than the degree. So max turning points is 1 less than the degree is what we want to put on that. All right, what observations can you make about how many times a linear factor of a polynomial function is repeated and whether its graph crosses the x-axis at the indicated x-intercept or is tangent to the x-axis at that point? So this is a good one. This is a good question. So if you'll notice here, it comes down here and basically just bounces off right there and goes back up. That's x to the 4th. X to the 3rd comes down and it does like a little wiggle through here and then minimums out and then goes back up. So this 4th, this was a bounce. The 3rd is a wiggle, W, sorry. And then this squared, right there, it bounces off and comes back down. So this x squared is a bounce as well. So what you want to kind of look at there is if it's an odd power on that factor, it's going to wiggle. If it's an even power on that factor, so x squared and x to the 4th, it's going to bounce. Okay? Okay, so odd power, wiggle, or cut, because like if you notice this is x to the 1st, so these are odd powers and those just cut straight through. And then when it's a cube or a 5th power or whatever, it's going to wiggle. Kind of goes, kind of wiggles through there at that point of inflection. Okay? D, for polynomial functions for which the domain is all real numbers, will the graphs of cubic functions have a global maximum or minimum? Will the graphs of quartic functions have a global maximum or minimum? So if it's a cubic function, like basically cubic function is positive one's going to look something, well, let's see. Let's do this. Cubic, so it could look something like, say that, but it's going to end up, it's only going to have 2 possible turning points. So it's going to go forever and ever down, forever and ever up. So that means for, let's see, odd or cubic. So cubic, no max, or well, really global max or min, right? Global max or minimum. But then a quartic, if you'll look here, notice these are all finishing up. If any of these were negative out front, they would all start down below and they'd end down below. Okay, so quartic functions will have a global max or minimum. Okay, global maximum or minimum. It won't have both. Can you extend your reasoning for these functions to polynomial functions of a greater degree? Pretty much all the odd ones are going to always only have, like, let's say if, so this is a cube, x cubed. If it was x to the 5th, we could go say 1, 2, 3, 4, starts They're going to end up going opposite directions. X to the 7th is going to have a couple more wiggles in there, but it's going to end up opposite directions. Whereas all the even ones are going to end up either both like starting with a like having a starting up and ending up, or starting down and ending down. Okay? Odd functions do not have a global minimum or maximum. Even functions will have a global minimum or maximum. Okay? All right, that's all we're going to do for the first part of this section here, and we'll do another one. But if you have any questions on any of this, please feel free to ask in class. Thanks.